Okay, so I'd say let's get started. Maybe Andrew and Klaus, if you can mute um, your mics. Okay, so welcome, aloha, and welcome everybody to today's defense by Larissa Nofi. For those of you who don't know me, I know we have probably a bit of a broader audience today. My name is Stan Huber. I'm the chair of the committee, and I'll be moderating today's proceedings. So just as a sort of logistical background, we'll have a talk by Larissa, which will last about 40 minutes. After the talk, there will be time for questions by everyone who's online. The questions we will handle preferably using the raise hand feature in Zoom. So if you have a question, please use the raise hand feature and we'll call out your name and you can ask a question. If you can't find the raise hand feature, you can also use the chat room. That will also be available, so you can type your question in the chat and I can then read it out. But I'll make another reminder of that after the talk. And we'll wrap things up at about at the hour, roughly. And then I'll ask everyone but the committee members to leave the Zoom room so we can have a closed session with the committee and Larissa. So before I hand it over to Larissa, I'm gonna, in the tradition of the IFA, give a brief sort of review or background as to the path of Larissa through grad school to today of her day of her thesis defense. So the path of Larissa started in San Francisco, the City College of San Francisco, and I think Larissa mentioned that in fact some of her earliest mentors are online with us today, listening in to her defense. So welcome to everyone dialing in from San Francisco. She then moved a little bit further down the bay to Santa Cruz, at UC Santa Cruz, for her undergraduate degree, worked on polarimetry of exoplanets, did observations at Lick Observatory, and then finally, of course, joined us here in the graduate program at the Institute for Astronomy at the University of Hawaii in 2014. So like all grad students here, our grad students in Hawaii go for various adventures during their years in Hawaii. I have some pictures that document this a little bit, with big thanks to a special friend of Larissa's. It'll be very obvious who it is in a second. So one of the things, of course, that our graduate students go for is a trip to Mauna Kea to see the telescopes in Mauna Kea Observatory. That year, for the class in 2014, it turned out to be a particularly adventurous trip, I heard. Included a flat tire that you see here on the left on the way up. The beast, by the way, here is not referring to the wrench that they used to actually fix the tire, but it is referring to the assignment by Mike Liu from Astrotech that they received, which apparently was so overwhelming that it got the nickname the beast. So Mike, if you're online, then if you didn't know already, it was a beast of an assignment, at least back then. So it helped with the flat tire, but eventually they made it up to the summit, and I can see them here in front of Gemini on the summit of Mauna Kea. And of course, as part of any trip to the Big Island, of course, also it's a trip to the beach. So you can see Larissa here down at the beach at I think Waipio Valley on the Big Island of Hawaii. So as any graduate students, go for ups and downs, and I was no different in Larissa's path. So here are a few pictures that document the ups and downs, which included surviving an apparently frigid office that we put our graduate students in here on the left. I'm not sure if that's still the case, but apparently, at least in 2014, you needed a sleeping bag to survive. It also included participating in the annual Halloween competition, which in this case was decided to be standing up for the rights of dwarf planets. And then finally, of course, on the right, you see the graduate students after passing the qualifying exam, which is, of course, one of the big hurdles in the life of a graduate student. So after passing the qualifying exam, of course, the next step is to actually decide on what you do for your thesis project. And Larissa decided to stay with her passion in exoplanet science and proposed a thesis to search for young planets around T-Tauri stars. This is an image from her thesis proposal, which was in early 2017 at the IFA, still in person back then, of course. It was a large audience. One of the audience members that you see down here, some of you will recognize him, Ollie, was particularly excited by the thesis proposal and slept through it. of course, did not necessarily ask the toughest questions, but we were excited about the audience was excited about the proposal and the work that followed. And in fact, to pursue this work, Larissa moved to Arizona, to Lowell Observatory, to pursue the observations, which included the Discovery Channel telescope that you see here, and an instrument mounted at the DCT, which Larissa will tell you all about in her talk. So for the next 3 years, Larissa obtained the observations, reduced the data, and analyzed the data, and analyzed the results. And in early 2020, Larissa moved back, Larissa and her husband moved back to Hawaii for the final sprint of her thesis work to analyze the data and wrap it all up. Of course, as many of us know, early 2020 was also exactly the time when the world changed because of the pandemic. And in fact, if you look at the number of cases, COVID cases, as a function of time in Hawaii, Larissa basically moved back to Hawaii for the second time, right at the start of this, when it started. At the beginning, actually, Hawaii was not a bad place to be, but now, as we all know, it's gotten a bit more serious. But I'm showing this just to illustrate that, of course, this is all a difficult time for all of us, including our graduate students that are working on various topics, including writing up a thesis during these extraordinary times. And of course, at the beginning, we were still able to meet in person a few times. We just talked about this a little bit earlier. But then for the rest of the time, most of the meetings were remotely, including a group meeting. So this is a shot for one of our group meetings that Larissa has been participating in, sharing her results and getting input from the group to help along with the final sprint towards finishing her dissertation. So during this time as well, Larissa successfully applied for the next step in her career, and that will be a position as an astronomer at the Aerospace Corporation in Los Angeles. I know she was very excited about the position, and we were excited that it worked out. And that will actually be starting quite soon, in October, next month. And I guess it will start remotely, but hopefully once life gets back to normal, the cycle will close and Larissa will basically return to California. Okay, so that is all I wanted to say. That is sort of as an intro, the path of Larissa through the point where we are today. So I'll stop sharing and I will hand it over to Larissa to tell us all about her thesis research.
Okay. Thank you for that introduction, Dan. That was great. Let me share my screen here. All right. Well, thank you everyone for joining me today. I'm really excited to be sharing my research with you. I'm going to be talking about a survey to search for young substellar companions using infrared spectroscopy. So the aim of this survey is to find young substellar companions, such as short period brown dwarfs and short period gas giant planets, where brown dwarfs are objects that have a mass between that of a gas giant and a star. And in doing so, the survey also aims to provide insights into the question, what is the origin of close-in substellar companions? So here I'm showing a diagram of the planets that have been detected as of 2000. This is a diagram that shows the lower limit on the companion mass versus the orbital period. If you look at this diagram again with all the exoplanets discovered 20 years later, you can see that we see these very distinct populations of exoplanets that are very different from those observed in our system. I've included Jupiter and Earth here for reference. A particularly interesting population are the hot Jupiters. These are gas giant planets with an orbital period between 1 and 10 days, and also the warm Jupiters with an orbital period up to 100 days. So a really interesting thing about these populations is that we don't necessarily know how they formed so close to the host star. One idea is that they formed further out in the system and then migrated inward through interactions with the disk, or through interactions with a third body, like another planet or another star, through high eccentricity migration. There have also been some scenarios put forth for in situ formation. However, it is very difficult to form a gas giant planet core at the high temperatures close to the host star, and there is less material in the inner disk. Close-in brown dwarfs are also a really interesting population because of the brown dwarf desert. This is a region typically defined within 3 AU, corresponding to an orbital period of 5 years, in which we observe very few brown dwarf companions around solar-type main sequence stars. So here I'm showing a diagram, again, of companion mass and orbital period, and you can see that there have been several planetary detections and stellar companion detections, but very few short-period brown dwarfs. And the different shaded regions just correspond to different sensitivities. So a question we can ask here is the brown dwarf desert caused by formation, as in do these brown dwarfs just not form at these short period orbits, or is it caused by later evolution? So in order to understand the origin of substellar companions, it's important to study the planet statistics. So we know that hot Jupiters are quite rare in main sequence systems with an occurrence rate of 1 to 2%. Warm Jupiters are a little more common by a factor of about 2 to 4, but close-in brown dwarfs are very rare. However, we do not know if that is the case for pre-main sequence systems, and evidence suggests that the occurrence rates may actually be higher. This is in part based on candidate discoveries in surveys with relatively small sample sizes, and also simulations that have shown that hot Jupiter formation rates may be as high as 40%, with survival rates up to 15% during the time of disk migration. Another study suggests that young brown dwarfs in short period orbits may be more prevalent in pre-main sequence stars, and then over time be destroyed. Brown dwarfs and hot Jupiters may be destroyed if they're migrating inward and do not experience a stopping mechanism, so they could be consumed by the host star. They can also be destroyed by tidal forces, such as Roche lobe overflow. This can also lead to extreme mass loss, also coupled with stellar irradiation. Or they could be ejected from the system. So this is some evolutionary factors as to why we may observe a higher occurrence rate in pre-main sequence systems. So if it is in fact higher, if the occurrence rate is higher in young systems, this suggests a formation mechanism that happens on the time scale similar to the age of the systems that we observe. So this would favor disk migration. So this has to happen on the time scale before the disk dissipates, usually 1 to 3 million years, but can be up to 10 million years. It also suggests a destruction time scale that is greater than the age of the system, and it would suggest that the brown dwarf desert is caused by later evolution. If the occurrence rate is lower in these young systems, this would favor a formation mechanism that happens on a time scale larger than the age of the systems, such as high eccentricity migration, which can happen on the orders of hundreds of millions of years to over a gigayear. It would also suggest that the brown dwarf desert is intrinsic to formation. So let me talk a little bit about the survey and how I detect young substellar companions. This survey relies on the radial velocity or RV technique. Essentially, when you have the planet orbiting around a star, the star is orbiting around the system's planet of mass. We can detect the motion towards and away from us as a redshift and a blue shift in the spectrum. Translating this to radial velocity versus time, see this RV curve. And based on this, the amplitude of this curve, we can determine a lower limit on the planet mass as long as we have a stellar mass. And we can also determine orbital parameters. So there are some challenges with finding young substellar companions because of the pre-main sequence stars. First of all, they're typically very far from us, and therefore they're oftentimes faint. Many of them still have a circumstellar disk, and so you have phenomena such as accretion from the disk onto the surface of the star, and that can create some radial velocity variability. In particular, though, they have high levels of magnetic activity, and this also creates RV variability. So if you see a comparison here at the inset image of the sun, you can see that it has some small sunspots on it. And comparing that to this artist's illustration of a pre-main sequence star, you can see that there's dramatically more stellar activity effects and larger star spots on the surface. So these star spots can live for hundreds of days, and they can cover up to 80% of the host star surface. So the star spots in particular are problematic. This animation illustrates what they do to the variation of the intensity profile of a spectral line. And essentially this translates to RB variation that could mimic a planet signal. So one way to mitigate this is to move into infrared light. So the diagram on the left shows the different contrasts between the temperature of the star, shown in blue, and the temperature of the star spots, shown in red. And you can see that as you move to longer wavelengths, the contrast is dramatically decreased. So this translates to less RB variation, which is shown in the bottom right. If you just look at the visible light RBs, shown in blue, this looks like it could be a planet detection. However, by moving into infrared light, you can see that that amplitude decreases. And so what we're observing here is actually a heavily spotted pre-main sequence star. So the science objectives of the survey, first of all, are to detect or confirm and characterize young close-in companions and place upper limits on their occurrence rates. With infrared spectroscopy, we can also characterize potential pre-main sequence host stars and provide observational evidence that may be extended to both formation and evolution theory and planet statistics, and may be used for the basis of future surveys. So I collected my data using the high resolution infrared spectrograph IGRINS, which was a visiting instrument for 3 observing seasons at the 4.3 meter Lowell Discovery Telescope. The telescope is shown here, and IGRINS is the gold instrument mounted on the base. So this instrument has a resolution of 45,000, and it simultaneously observes both the H and K bands in the near infrared. And it's a stable instrument because it has no moving parts. I initially chose 70 targets for the spectroscopic characterization. 10 of those targets I chose for the radial velocity survey. These stars typically have an age between 1 to 5 million years old, and they're located in the relatively nearby Taurus star-forming region. I limited the sample to stars of spectrotype K and M, so these are low mass stars, which have signal to noise ratio that peaks in the red and infrared part of the spectrum. And they're relatively bright with a magnitude between 7 and 9. They're also primarily slow rotators, and this ensures that we have very deep and narrow lines for the accurate RB analysis. And about 70% of them are classical T-Tauri stars, meaning that they still show evidence of having a disk based on equivalent widths of H-alpha observation. About 45% of them are in multiple systems. I observed these targets over 67 nights over the course of 3 observing seasons. However, I did lose 27 nights given technical difficulties or weather losses. I have about 1,000 total spectra, and about 500 of those are for the follow-up radial velocity survey. And I do want to note that the follow-up observing season, the final season of the IGRINS observations, did have a lower resolution. Instead of 45,000, it was about 20,000. And this was due to some loose detectors in the K-band detector mount. So this only affected the region in the K-band. Here is an example of some reduced K-band spectra. These cover the 3 observing seasons. This is all the same star. And you can see again at the bottom that the resolution is a little lower. So this is the region that I use for my analysis, both to characterize the host star and to do the RB search for substellar companions. I've indicated here by the arrows, the stellar lines shown in red and the telluric lines, which are absorption lines from the Earth's atmosphere, shown in blue. The stellar lines are primarily caused by CO, and the telluric lines are mostly caused by methane. So using the infrared spectroscopy, I characterized some stellar properties of the pre-main sequence stars, and I worked with some collaborators on this. The main focus of this study was to find the projected rotational velocity, or the v sin I, and this is an important parameter also to determine the radial velocities for the program that I used. And so I measured the v sin I using a standard cross-correlation technique. And here I'm showing some example spectra, basically just to illustrate that higher v sin I, the spectral lines become broader, just as we would expect. A collaborator also provided optical v sin I's for a subset of the data, and effective temperatures from the line depth ratios, also using the Eigen's data. And I also included the photometrically derived stellar rotation periods. And using these parameters, I could then place limits on the stellar radius. So let me talk a little bit about the results of characterizing these pre-main sequence stars. What I'm showing here is a histogram of stars in single systems and stars in multiple systems. And these are the v sin I distributions for those two populations. And I found that the binaries and multiples typically have a higher measured v sin I. So this could be caused by evolution. Stars in binary systems may have their disks truncated or have short-lived disks. And without those disks to magnetically break them, they may spin up. However, this could be evidence of companion contamination, where there's line blending from light on the spectrum slit from another star. I also compared the infrared and optical v sin I values and showed that they statistically match. This isn't just comparing the same data set, but with two different wavelength regimes. There was also some differences in how we analyzed these. But what I was looking for in particular was if there was any significant impact of CO emission in the disk, which we would expect to detect in the infrared, but not the optical. And so I looked individually at both the classical T-Tauri stars, which show evidence of having a disk, and the weak line T-Tauri stars, which likely don't have a disk or have a very tenuous disk. And I did not see any significant impact of disk CO in the infrared data. And this is also really important for the RVs because we want to make sure that we're not detecting a significant contribution from the disk, the CO in the disk. I also compared the v sin I distributions of the classical T-Tauri stars and weak line T-Tauri stars. My analysis is shown in the top panel, and I found that these were statistically different. So what we would expect from theory is that classical T-Tauri stars should be slow rotators because they still have a disk. They're going to experience magnetic braking, and this will slow them down. However, once the disk dissipates and they become weak line T-Tauri stars, over time they will begin to spin up because they are still contracting. And so we would expect to see a wide range of v sin I's for weak line T-Tauri stars. And that appears to be what I saw in the data set. However, it's also possible that this is a selection bias given the way that my sample was chosen. So to resolve this, I also looked at the Nguyen et al. 2012 values from the literature, and those v sin I's are shown in the middle panel. They did not find a statistically significant difference between those two v sin I distributions, and combining their data with mine shows that this is likely a selection bias effect. I also plotted the targets on an HR diagram. Here I'm showing the classical T-Tauri stars as circles and the weak line T-Tauri stars as squares. The colors indicate the v sin I. And just to remind you all, these targets, these pre-main sequence stars migrate down onto the main sequence. The gray X's indicate the Pleiades targets, and so I used this as a rough approximation for the zero-age main sequence. So I did not see any clear correlation between the HR diagram position in either the v sin I or the classification. And so this suggests that stellar rotation and evolution is both complex and varied, and that we need to know more about a star to understand its evolutionary state. So these planet properties were submitted in a paper to AppJ. I worked with collaborators here at the IFA, at Lowell Observatory, University of Texas at Austin, and at Rice University. Okay, so let me talk a little bit about the RV analysis method. To calculate the RVs, I used the forward modeling technique. This is where I took a stellar model created from next-gen stellar atmosphere models, and I combined it with a telluric template from NSO observations, and that's shown in panel A and B. I then fit the combined model to the observed spectrum, which is shown in red, and the residuals are shown in D. I then measured the shift of the stellar lines relative to the telluric lines. So the telluric lines serve as my wavelength reference. I used a modified version of a program that was developed for the instrument Seashell, which was previously on the IRTF. This optimizes a set of parameters. First, the stellar RV. The telluric RV remains fixed at 0 because that is the wavelength reference. It also optimizes velocity scaling factors, which correspond to the depth of the absorption lines. The V sin I is also fixed because I calculated that also with the iGrens data and increased the efficiency of the code. However, the V sin I is not the only factor that causes broadening of the spectral lines. There's also the instrumental profile full width half max, which is related to the resolution of the instrument. So I determined this property and also had the program optimize that value. And lastly, it optimizes coefficients that describe the continuum and wavelength solution. So the way I determine my survey precision is by observing a radial velocity standard star, GJ281, every time I was at the telescope. This is an RV stable star, and so it should have the same measured RV every time that you observe it from night to night. So any deviation in the RVs can be attributed to the method as a method uncertainty. I had a starting precision of 130 meters per second, looking at a single order in the K-band. On the upper right, I'm showing a diagram of this order. If I restrict the region to just the red spectrum and trim the edges, then I avoid the distortion at the edges and the regions of low signal to noise, and that improves the precision. Also, I was able to improve the continuum fit. The original spectrum fit is shown in black in the bottom, and the green shows the improved fit. One of the challenges with this region is this heavy set of absorption features, primarily telluric lines at about 2.318 microns. That can make it a little challenging to fit the continuum. So these improvements made the precision better from 130 meters per second to 70 meters per second. So here I'm showing the RVs of the standard star GJ281, so you can get an idea of the variation. As you can see, the final season has larger scatter because of the lower resolution. And the precision for the final season is about 115 meters per second. So this can give us an idea of our survey sensitivity. However, we can also get that from injection and recovery simulations. So I used a tool called RV Search from the team at Caltech, and it's described in Howard and Fulton 2016, basically to determine the completeness and the sensitivity and to place upper limits on occurrence rates. I ran injection recoveries with 1,000 simulations, and here is an example of the output for the RV stable star GJ281. So this is an example of our sensitivity for a main sequence quiet star. So this shows the lower limit on companion mass versus semi-major axis, and I just want to note that the mass is in Earth masses. 1,000 companions were injected into the RV data set. Those that were recovered are shown as blue circles, and those that were not are shown as red circles. And then the contours indicate the probability of detection. So let me talk a little bit about the results of the RV survey. that is searching for substellar companions. The first target of interest was Ci Tau. This is a 2 million year old classical T-Tauri star. It was noted as having a hot Jupiter candidate in Johns Crow et al. 2016, as indicated by their periodogram analysis, which found a peak period at 9 days. They used a combined data set of infrared and optical spectroscopy. So the RVs based that period are shown in the bottom plot. The optical are in pink and the other infrared instruments are shown as the colored points. They determined a probable mass of 11 Jupiter masses. Biddle et al. In 2018 also looked at the K2 photometry of Ci Tau, which is shown on the bottom. It's the light curve and their periodogram analysis. They also detected a 9-day period and suggested that this is evidence of star-planet disk interactions. It is not expected that this companion would be transiting. Flagg et al. In 2019 also noted a 5.7 sigma detection of CO in the system, which they attributed to the planet atmosphere. However, Donati et al. In 2020 also detected this 9-day period. They showed that the RVs phased very well to that. However, based on correlations between the period and between the activity indicators and the data, they suggested that this is actually a stellar rotation period and not a companion orbital period. So looking at the infrared data here, I had 74 observations with IGRENs, and this is the periodogram analysis. I used a standard Lomsgargle periodogram analysis, which is ideal for unevenly sampled data. And I used a bootstrap method for the false alarm probability. So I've indicated the 9-day period in the red dotted line. And I do see some excess power here. However, it's at a false alarm probability that's greater than 5%. So this is not a statistically significant detection. I've also noted the various possible stellar rotation periods from the literature as yellow dotted lines. It is difficult to determine a rotation period for this star from photometry because of the large amount of accretion in this system, and that causes a lot of photometric variability. So I don't see strong evidence of the 9-day period in the periodogram analysis. Now looking at the injection recovery completeness contour plot, I've indicated here the brown line showing the boundary between low mass stars and brown dwarfs, and the yellow dashed line as the boundary between gas giant planets and brown dwarfs. And then the light blue line indicates a 1 Jupiter mass planet. The black circle indicates the candidate at the properties reported by Johns Crow et al. Using the most probable mass. But if I assume the minimum mass of 8 Jupiter masses, the detection probability is 86%, and it's 93% if I assume the probable mass. This is all assuming a false alarm probability detection threshold of 1%. If I decrease that to a more conservative detection threshold of 0.1%, I see a probability of detection between 70 to 90%. So I don't see evidence of the companion in the completeness contour plot, but I do want to note that there is convincing evidence of a 9-day period in the system from the literature. I'm showing here again the periodogram analysis from optical and infrared RVs, optical photometry, and also the RVs from Donati et al. 2020 modulated to the 9-day period. However, more data is needed to confirm that this period is planetary in origin. Another priority target was B830 Tau. I had 87 observations of this, and the RVs versus time are shown in the top panel. This is a 2 million year old weak-line T-Tauri star, and it also has a reported candidate around it, B830 Tau B, which has a reported mass of 0.8 Jupiter masses, and it's in a roughly 5-day orbital period. So my periodogram analysis is shown in the middle panel. The dotted line just corresponds to where I would expect to see harmonics in the data set. And you can see that there's a statistically significant peak that meets the 1% false alarm probability threshold at 2.74 days. Now, this is likely the stellar rotation period, which is indicated by the yellow dotted line. It has been reported in the literature as being 2.74 days, and the K2 data confirms that. The bottom panel shows the RVs phased to that 2.74 day period, and the red points indicate thinned RVs. The orange line shows the sinusoidal fit. So I likely detected the stellar rotation period in this system. Here I'm showing the completeness contour plot for this target. The gray circle indicates the candidate V830 tau B. Now, an independent study was unable to confirm V830 tau B. This was Damaso et al. 2020. We did not expect to, I didn't expect to detect this companion, either confirm it or refute it, because of the sensitivity of my system and the fact that the RV semi amplitude is 60 to 80 meters per second. However, I do want to note that using these completeness contours, we were able to place limits on what we did not detect. And so non-detections are also very informative for that reason. Another target that I looked closely at is DK tau. I had 54 observations of this one, and I also detected a statistically significant period at 8.17 days. The motivation for including this target is that it had some similar features as CI tau, as quoted in Crockett et al. 2012. So it may have been may have also had a companion around it, and so I included this in the intensive list to look into the RV analysis of optical and infrared data. There are various stellar rotation periods quoted in the literature, again, because of accretion in the system. 8.18 days is one of the stellar rotation periods from the literature. And so again, I likely detected a rotation period of the star in this case. This is the completeness contour plot for DK tau. Now, one thing to note here is that it has far less sensitivity than the other target data sets. And so there's a wide variability in the sensitivity, partly because of the number of observations, but also because of the amount of RV scattered in each system. And these are the remaining targets in the data set. I did not have any detections of substellar companions with these targets. B1075 tau was chosen because I initially saw some infrared RV variability. However, I did not detect anything with additional data. The K2 targets are also shown here. So these were targets that were observed by K2. And in collaboration with Lauren Biddle, I observed them so that we could work together on, so that she could analyze them for star-planet disk interactions. So these are their RVs, and these are their completeness contours. And again, I just want to show that there's a wide variation in the amount of sensitivity for each of these data sets. So I'd like to take a moment to talk about the survey sensitivity and the upper limits that I've placed on occurrence rates. So this is showing the RV stable star GJ281 again. This is the completeness contour, and I've indicated the boundary between brown dwarfs and stars, that's the black line, and the boundary between planets and brown dwarfs is the gray line. The light blue region indicates the general survey sensitivity, where we're sensitive to planets with masses greater than 6 Jupiter masses and brown dwarfs within about 1 AU. To give you an idea of the variation in that sensitivity, I'm also indicating with the blue squares, the lowest mass companions that I could detect in these systems, from 2 Jupiter masses to 15, in which case, for that target, we weren't sensitive to planets. And this indicates how far out we could observe a companion. It ranged between 0.04 AU to 0.8 AU for planetary companions, and between 0.5 AU and 2 AU for brown dwarfs. Now I'm showing these again. This is the full data set, the completeness contours. Again, you can see that the level of sensitivity varied quite a bit for each of these targets. So using this sensitivity, I can place upper limits on occurrence rates. So the way that I did that is I made a grid of companion masses and semi-major axes. Based on the sensitivity in each individual target data set and the number of non-detections, I could then place an upper limit on the occurrence rate. So this figure shows the results of that. The colors and the numbers indicate the percent on the upper limit of occurrence. And the cross-hatched region is a region of parameter space that my survey is not sensitive to. And I also want to note that these upper limits on occurrence rates apply to stars similar to those in my sample. So I've listed their parameters here. So considering just the planets, the upper limits on occurrence rates are 25 to 50% for high mass hot Jupiters. If I compare this to the 1 to 2% occurrence rate in the main sequence, I see that this is consistent with theory that predicts a higher occurrence rate based on candidate discoveries with small sample sizes and simulations that show formation rates of hot Jupiters between 8 and 40% with survival rates of 3 to 15%. This also suggests that destruction timescale would be larger than the age of the system and that the formation mechanism may be disk migration, that may be the favored mechanism. However, I do want to note that these are upper limits, and so it's also possible that the occurrence rates are as low as those in the main sequence. And so we need more data to be able to say. Looking at the brown dwarfs, I also see upper occurrence. I determine upper limits on the occurrence rate of 10 to 50% for close-in brown dwarfs. Again, this could suggest that there are more brown dwarfs within the brown dwarf desert that form, but then don't later survive. However, because they're upper limits, I cannot rule out that they are also quite rare in pre-main sequence systems. So I also looked into correlations between the RV scatter and system properties. Here I'm showing a histogram of the RV scatter of these 10 targets. The average infrared scatter was 550 meters per second. This is about half that of the typical optical RV scatter of 1 kilometer per second for stars of ages between 1 to 3 million years. So this basically illustrates nicely why you want to do a survey like this in infrared light, where you're going to have less RV scatter caused by other effects in the system. Here is a table showing all 10 of the targets with their RV scatters in meters per second, but also some of their stellar properties, such as the V sin I and their classification as either classical T-Tauri star or weak line T-Tauri star. So I looked for some correlations with system properties. And one thing I noticed is that the average RV scatter for the classical T-Tauri stars is very similar to that in the weak line T-Tauri stars. And so this suggests, since one population has accretion from a disk and the other doesn't show evidence of that, this suggests that stellar activity may be a major factor for RV scatter. However, stellar activity is also closely linked to rotation, where faster rotating stars have higher levels of activity. And I did note that DM tau, which had the lowest RV scatter, also has the lowest V sin I. And the 2 targets with the highest V sin I were the weak line T-Tauri stars, which also had high RV scatter and do not have contribution from a disk. I also looked into whether there's a correlation with disk features. I noted from the literature that DM tau and calcium-15, which both have relatively low RV scatter, both have evidence of inner disk cavities. And IQ tau has a high level of accretion. Based on the photometry data, this indicates that this is a heavy accretor, and it has a high level of RV scatter. So there very well could be a contribution from the disk. And I just want to note, DK tau was the outlier with the RV scatter of 1.1 kilometer per second. This is a binary system. The companion is at about 340 AU separation, and they have misaligned disks in the system. So there could potentially be a correlation there. And just to summarize, first of all, the primary aim of the survey is to detect and characterize young substellar companions and to set upper limits on the occurrence rates. Another goal is to detect and characterize young substellar companions, which is, it's also very important to do so because then we can test information, formation and evolution theories. An infrared survey is less susceptible to RV variation caused by star spots. Now, looking at the stellar characterization, particularly the V sin I, I noted that the pre-main sequence star V sin I distributions indicate a higher V sin I was measured in multiple systems, which could be caused by evolution, or it could be an effect of contamination from a companion. There is likely no significant impact of disk CO in the infrared data based on comparing the optical and infrared classical and weak line T-Tauri star V sin I measurements. And I likely detected a selection bias rather than a feature of evolution, which caused the difference in the classical and weak line T-Tauri star V sin I distributions. I also did not find a clear correlation between HR diagram position and the evolutionary state. Here's a summary of my results. While there is convincing evidence of a 9-day period in the CI tau system, additional study is needed to confirm whether it's planetary in nature. And I detected the likely stellar rotation periods in the two systems, BA30 tau and DK tau. They did not make any further detections in the remaining data set. The survey is generally sensitive to planets with mass greater than 6 Jupiter masses and brown dwarfs within about 1 AU. Upper limits on the occurrence rate of high mass hot Jupiters was found to be 25 to 50%. And close-in brown dwarfs, the occurrence rate was 10 to 50%. And this is consistent with evolutionary theory that predicts higher rates of occurrence, but we also cannot rule out rates that are lower or consistent with the main sequence. Looking at the RV scatter, I determined that the infrared RV scatter is about 2 times lower than the typical optical scatter. I also showed that stellar activity and rotation in the presence of a disk may contribute to RV scatter in the infrared data, that there may be a correlation there. So continuing this work in the future, it's possible to conduct an RV survey like this using other high resolution infrared spectrographs, such as iShell at the IRTF, the RED at Subaru, and SPARU at CFHT. RV and transit methods are also very complementary, and TESS has observed some young stars. And so transit methods measure the planet radius and RVs measure the planet mass. And so they can also be used, RVs can also be used to confirm transit detections. An RV survey is sensitive to close-in high mass objects, and so it's also very complementary to use with direct imaging surveys, which are sensitive to distant gas giant planets in young systems. So combining an RV survey with direct imaging surveys and with ALMA, which can image disk structure, can connect inner and outer system planet formation. Also, additional characterization of infrared RV scatter is necessary to better understand the sources of scatter. Combining methods can also be very useful, such as optical and infrared RVs, to compare their amplitudes, and also to determine stellar rotation periods using photometry. So with that, I just want to take a moment to say some acknowledgements. I'm very grateful to my advisor, Dan Huber, and to my committee, and to the IFA, everyone at the IFA. There's too many people to name here. I'm also grateful to my collaborators at Lowell Observatory, University of Texas at Austin, Rice University, and the Caltech team that shared our research with me. And I'm grateful to the observing staff at Lowell Discovery Telescope for all the assistance in getting all this data. And I also want to acknowledge people who have supported me in my research before going to graduate school. People at University of California at Santa Cruz, Lick Observatory, and my professors at City College of San Francisco, who first got me interested in astronomy. So thank you, everyone. With that, I can take questions.
All right, thank you, Larissa. So I think you should now be able to raise your hand if you have a question or type it into the chat, although preferably raise your hand. Kurt, oh yeah, there you go. Jamie has a question. Go ahead. I think you need to be unmuted by Kurt. Hopefully you can see you. Kurt, are you there? All right, I think perhaps Jamie, if you can type into the chat, maybe we'll do that instead. I think we're supposed to be able to unmute people in the attendees section, but I don't think this is working right now. Kurt, are you there? Okay, maybe not. Okay, there you go. There's a question. So Jamie has typed a question. Given the relatively low detection rates, how many stars would you realistically need to survey to detect 1 or 2 planets?
Oh, yes. So given our survey sensitivity, if we want to, the question is how many we would need in our survey to place meaningful limits. Essentially, so in order to determine whether or not the occurrence rate, say for hot Jupiters, is higher than that in the pre-main sequence, we would need more than 100, or I'm sorry, if the occurrence rate is higher than that in the main sequence, we would need a survey of more than 100 targets to get an occurrence rate that is at the 1% level. And I also want to note that this would be a big survey because we do need a lot of data on these targets because of the large amount of RV scatter we typically see in these systems. We do need something like 50 to 100 observations, but it's definitely an exciting path for the field going forward.
Okay, we have a question from Stuart Jeffries. You pointed out the challenges with observing at optical wavelengths, but are there any advantages for detecting planets at optical wavelengths as well?
Oh, that's a good question. You mean just for detecting young subsolar?
Yeah, I think for detecting any sort of planet, but perhaps for the young stars in particular, but perhaps for detecting any sort of planets in general.
Well, for these systems, at least, where there's so much scatter caused by star spots and other phenomena related to the disk, infrared definitely is, I think, the preferred method. Optical definitely has a place here, though, because we can compare amplitudes of optical RVs and infrared. If there's a large difference between those amplitudes, then that suggests we're seeing effects of stellar activity. If they're similar, that would suggest a planet detection. So optical RVs are definitely useful for finding young planets. And it is the primary choice for main sequence systems. So.
Okay, I see people are getting have now a symbol next to them that says talking permitted. So if anyone has a question, please still raise your hand if you have one, so we can unmute you. But you should be able to work now, in addition to the written questions. Okay, any more questions from non-committee members? Trying to scan so I don't miss anyone. Okay, going once, going twice. All right, if not, then I will, let's thank Larissa again for the talk. And I'll ask all the non-committee members to sign off from the Zoom.